Hey, it's Mr. Shrum again, and I'm back with a physical science tutorial, and we are looking at the electromagnetic spectrum today. So we're going to describe the electromagnetic spectrum, and that's about it. So let's get into it. This man is James Clerk Maxwell, and he is the first person in the world to figure out that light was an electromagnetic wave. He was a British scientist in the mid-1800s who began his work in the then new sciences of electricity and magnetism. He found how electric current and the magnetic field were related. He saw that these two continuously interacting changing fields at right angles to each other generated electromagnetic waves. Since these waves consisted of fields in space and not an interaction of matter, they didn't require a medium to propagate and could travel through the vacuum of space. His concept of what waves are was revolutionary. He also developed a formula to calculate the speed of electromagnetic waves, 2.998 times 10 to the 8th power meters per second, the same speed as which light travels. After that, it didn't take him long to discover that light is a form of electromagnetic waves with a frequency observable by the human eye. His discovery that light is a wave is important. Visible light is important to the entire planet since it provides energy for plants and animals to thrive. But it's just one form of energy and electromagnetic waves. Recall that energy exists in different forms. One form is radiant energy. Radiant energy is the energy of electromagnetic waves, which travels through space in the form of electromagnetic radiation. Visible light, X-rays, radio waves, and the microwaves in a microwave oven are all examples of electromagnetic radiation. These different forms of electromagnetic energy share similar properties. And here we're going to study the types of waves in the spectrum and compare the frequency and energy of different electromagnetic waves. The quantum model states that electrons can jump from one energy level to another, from high to low or low to high. So example here, this electron is jumping up in energy, this electron is jumping down in energy. An electron in a higher electron level, farther from the nucleus, has more energy than one in the lower level. So the further away from the nucleus you are, the electron has a higher electron level. When an electron drops from a high energy level to a lower one, it emits a light energy called a photon. This is a little light particle. The kind of photon depends on how much distance there is between the original energy level and the energy level to which the electron drops. In a laser, the energy supplied to the atoms excite the electrons into higher orbits. The electrons emit photons when they return to their usual lower orbits. Fluorescent lights and neon signs are also examples of light energy. Light energy generated from the transition of electrons to lower energy levels is electromagnetic radiation, which behaves like a wave. So when this electron jumps to a lower energy level, a photon is also emitted. Let's review some wave basics. Look at the two waveforms shown here. Both start at the rest line from point 0, reach the highest point P, pass through the rest line again, reach the lowest point and then comes back to rest again. And this cycle repeats. The cycle repeats over and over again. The highest point of a wave is called the crest. So points P and R are crests, one right after the other. The height of P from the rest point, the rest line of a wave, is called its amplitude. And that's shown here. How high the wave is from the resting point, the resting line, is the amplitude. Notice the different amplitudes of the two waves. The distance between two consecutive crests, so from P to R, is one wavelength, and that's shown here. And note that the wavelength of the first wave is about 2.5 units long. So we're going 1, 2, 2.5, longer than that of the second wave. This one's about 1.5, so 1.5 units. A wavelength is represented by the Greek letter lambda. The number of wave cycles that pass through a specific point in a given time period is the frequency of the wave. The unit of measurement for frequency is hertz, representing cycles per second. Since the second wave has a shorter wavelength, it has a higher frequency than the first wave. The electromagnetic spectrum contains the spectrum of visible light and several forms of radiation that aren't visible. The visible spectrum consists of different frequencies of light corresponding to different colors. All colors in the visible spectrum combine to form white light, and we're going to see more about that later on in this lesson. The remaining frequency ranges in the electromagnetic spectrum are radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. In a vacuum, all waves in the electromagnetic spectrum travel at 2.998 times 10 to the 8th power meters per second, which is the speed of light. Examine the electromagnetic spectrum in detail. So here we have X-rays here, UV rays, visible light, infrared radiation, microwave, FM, AM radio waves, and then long radio waves. And if you pay attention to this, as you move to the right, there's an increase in wavelength. As you move to the left, there's an increase in frequency. So higher frequencies are shorter wavelengths, lower frequency, longer wavelengths. Electromagnetic waves are categorized by their wavelengths and frequencies. Wavelengths range from smaller than the radius of an atom to hundreds of meters. This table shows the regions of the electromagnetic spectrum along with their frequencies and wavelengths. So here we have radio waves. They have the lowest frequency and the longest wavelength. Microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Gamma rays have the highest frequency and the smallest wavelength, smaller than an atom, while radio waves are as long as a pen or as long as a football field. To repeat, in the electromagnetic spectrum, radio waves have the longest wavelengths, ranging from inches to longer than a football field. These waves, invisible to humans, have changed how people live. With the exception of light, you probably come across radio waves in your daily life more than any other type of electromagnetic wave. Television signals are carried by radio waves. They also carry signals from your cell phone, cordless phone, and of course, your radio. Radio waves can transmit conversations, music, pictures over millions of miles, all the way into space. And to learn more, we have this video on microwaves and radio waves. And you guys can watch that on your own. I don't want a copyright strike. Match each wavelength to the correct region in the magnetic spectrum. Drag the items on the left to the correct location on the right. All right, so we're testing our knowledge here. Radio waves. Okay, gamma rays, we know have the shortest wavelength. We know that X-rays are small, so that's about the size of an atom. We know radio waves are the longest wavelength. Up, 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 up. Microwaves are about the size of a period or the size of a pen. And then lastly, we have ultraviolet radiation, about the size of a virus. All right, so that's the first part of the tutorial. Next time, we'll get into the energy of electromagnetic waves. But until then, have a great one, and I will see you guys later.